In the previous videos, we have seen addition, subtraction, and multiplication in matrices. Now it's time to talk about division, or the so-called division, in matrices. To do so, let's recall some concepts regarding these operations. Subtraction is defined as the opposite of addition, in the sense that if we do both addition and subtraction, it would mean doing nothing. For example, in the real numbers, x plus 2 minus 2 equals x plus bracket 2 plus bracket negative 2, which equals x plus 0, which equals x, for all real numbers x. Here, we will call negative 2 as the additive inverse of 2, and also call 0 as the additive identity. The special property about 0 is that whenever any real number is added to 0, we get back the original number. In this case, negative 2 is defined as the opposite of 2, so that whenever we add 2 and then subtract 2 from any real number, we always get back the original number. We have a similar notion in matrices. For example, a plus b minus b equals a plus bracket b plus bracket negative b, which equals a plus the zero matrix, which equals a, and this is true for any matrices A and B. Again, we call negative b as the additive inverse of b, and the zero matrix as the additive identity. So negative b has the effect of cancelling the effect of adding b, and this works solely because we have the existence of the zero matrix, which has the property that whenever we add 0 to a matrix, we always get back the original matrix. Similarly, division is defined as the opposite of multiplication. In the context of real numbers, y times 2 divided by 2 equals y times bracket 2 times 1 over 2, which equals y times 1, which equals y, for all real numbers y. Here, we call 1 over 2 as the multiplicative inverse of 2, and 1 as the multiplicative identity. The special property about 1 is that no matter what number I multiply by 1, I always get back the original number. So multiplying by 1 over 2 has the effect of cancelling the effect of multiplying by 2, and this works based on the existence of the multiplicative identity. So in the context of matrices, in order to define an inverse, or more accurately, a multiplicative inverse, we have to first find a multiplicative identity. And it happens that the identity matrix I, which we have introduced before, satisfies this condition. A times I equals I times A equals A for all matrices A. This means that no matter what matrix we multiply to I, we get back the original matrix. So the identity matrix has the same property as 1 in multiplication. So it serves as the multiplicative identity in matrices, and that's exactly the reason why we call it the identity matrix. Having acquired the multiplicative identity in matrices, in other words, the identity matrix, we will now try to define a multiplicative inverse of a matrix, or just the inverse of a matrix for short. That means that given a matrix A, we want to find a matrix B such that A times B equals B times A equals the identity matrix. First, we need to make sure that A times B and B times A are defined. So, if A has size m by n, then B has size n by m. But if m is not equal to n, then A times B is the identity matrix of size m, and B times A is the identity matrix of size n, so they are not the same. So, to make sure that A times B equals B times A, we also need that m equals to n. In other words, both A and B are square matrices. So this motivates the following definition. Let A be a square matrix. A matrix B is called an inverse of A if and only if A times B equals B times A equals I. In this case, we write B equals A to the power negative 1, and say that A is invertible or non-singular. If A happens to have no inverse, we say that A is non-invertible or singular. Let's look at an example. Suppose we want to show that B, which is the matrix negative 2, 3, negative 1, and 1, is an inverse of the matrix A, which equals 1, -3, 1, -2. To do so, it suffices to compute A times B and B times A, and show that both are equal to I. Now, A times B is the matrix 1, -3, 1, -2, times the matrix -2, 3, -1, and 1, which equals the matrix 1, 0, 0, 1, which is indeed the identity matrix. Similarly, B times A, which is the matrix -2, 3, -1, 1, times the matrix 1, -3, 1, -2, which equals the matrix 1, 0, 0, 1, which is also the identity matrix. So A times B equals B times A equals I. In other words, B is an inverse of A. Let's look at another example. Suppose we want to show that the matrix A with entries 0, 1, 0, -2 is not invertible. Let's proceed by contradiction and assume that B, which is the matrix with entries A, B, C, D, is an inverse of A. By definition, we have A times B equals I. So the matrix 0, 1, 0, -2 times the matrix A, B, C, D equals the matrix 1, 0, 0, 1. The left-hand side is the matrix with entries C, B, -2C, -2D. Equating the corresponding entries, we have C equals 1 and -2C equals 0, which is a contradiction. This means that A does not have an inverse, so A is not invertible. Observe that A is not equal to the 0 matrix, but it is not invertible. And this is different from the real numbers, because whenever a real number is non-zero, it guarantees that A to the -1, in other words, the inverse of A, exists. So we have to bear in mind that for matrices, even when the matrix is not the 0 matrix, it is still possible that the matrix is not invertible. Now let's look at a theorem. If B and C are both inverses of A, then B equals C. In other words, if a matrix has an inverse, then it must be unique. This result is consistent with the real numbers. The proof is relatively easy. Since B is an inverse of A, we know that A times B equals I. Also, C is an inverse of A, means that C times A equals I. Now, we can write B equals I times B, which equals bracket C times A times B. Since matrix multiplication is associative, we can choose to multiply the latter two matrices first, so this equals C times bracket A times B, which equals C times I, which is just C. So indeed, B equals C. Now, we haven't yet talked about the conditions for a matrix to be invertible, and in that case, the method for computing an inverse. The next result will cover the 2x2 case. Suppose we are given a 2x2 matrix, A, which has the entries A, B, C, D. Then, A is invertible if and only if A times D minus B times C is non-zero. In this case, the inverse of A equals 1 over A times D minus B times C times the matrix D, -B, -C, and A. Let's first prove that the left-hand side implies the right-hand side. Suppose A is invertible. We assume for a contradiction that A times D minus B times C equals 0. We let B be the matrix with entries D, -B, -C, and A. Now, A times B is the matrix A, B, C, D times the matrix D, -B, -C, and A, which is the matrix A times D minus B times C, negative A times B plus B times A, C times D minus D times C, negative B times C plus D times A. Since we have assumed that A times D minus B times C equals 0, the top left entry and the bottom right entry are both 0, and the other two entries are also 0, so we get the 0 matrix. Since the inverse of A exists, we have B equals I times B, which equals bracket the inverse of A times B, which equals the inverse of A times bracket A times B. Since A times B is equal to the zero matrix, we have the inverse of A times the zero matrix, which is just the zero matrix. In other words, all entries of B are 0, so all of A, B, C, D are equal to 0. This means that A is the zero matrix, which is the contradiction, since the zero matrix is not invertible. Hence, A times D minus B times C is non-zero. The converse is much easier, because we already have a candidate for the inverse of A, so it's just a matter of checking. So we compute A, B, C, D times 1 over A times D minus B times C times the matrix D, negative B, negative C, and A. Note that 1 over A times D minus B times C is just a scalar, so we can take it out to the far left. The product of the two matrices gives A times D minus B times C, negative A times B plus B times A, C times D minus D times C, negative B times C plus D times A. The bottom left and the top right entries are both 0, and the other two entries, when multiplied by the scalar outside, are both equal to 1. So we get the identity matrix. Similarly, if we multiply 1 over A times D minus B times C times the matrix D, negative B, negative C, and A by the matrix A, B, C, D, we get 1 over A times D minus B times C times the matrix D times A minus B times C, D times B minus B times D, negative C times A plus A times C, and negative C times B plus A times D. So again, we get the matrix 1, 0, 0, 1. Hence, the matrix A is invertible with inverse 1 over A times D minus B times C times the matrix D, negative B, negative C, and A.